Let's study 10th standard ICSE physics, chapter 5a, lenses and refraction of light through lenses.
A lens is a transparent refracting medium bounded by either two spherical surfaces or one spherical surface and the other surface plane. By the way, this plane surface is also a part of a large sphere of infinite radius. But that's technical, not important, because imagining infinity is insanity. Now there are two types of lenses, convex lens and concave lens. Concave lens diverges the rays of light and it's thin in the center, whereas a convex lens converges rays of light and it is thick in the center. Now if we have both a convex and a concave surface, then again look at the thickness of the central region. If it is thick in the center and thin at the periphery, it's a convex lens, but we call it concave or convex. On the other hand, if it is thin in the center and thick at the periphery, then it will be a diverging lens. That is, it's a concave lens called convex or concave. So whatever diagrams are double ticked, you need to practice them. Now the action of the prism can be considered when we consider the lens as a combination of various prisms. The lens can be broken up into different prisms to study how refraction takes place through the lens. For example, a convex lens can be considered as a combination of two prisms and a rectangular glass slab. So here the ray of light bends towards the base, here also it bends towards the base. So that explains why there is a converging action here. In a concave lens, we have an inverted prism here and one prism here. The head is cut off, that's a frustum. Anyway, the light refracts again towards the base here and towards the base here. This one goes straight through the rectangular glass slab since the angle of incidence is 0. So this explains the divergent action of a concave lens. Now let's study some technical terms related to a lens. Now in the lens, this surface can be considered to be a part of a sphere, an imaginary sphere, and the center of that sphere is called the center of curvature. Since the lens is not perfectly symmetrical, you can see that the centers of curvature are at different distances from the optical center. Optical center is, you can consider as the midpoint of the lens. We'll define it soon. Now, the line, imaginary line joining the two centers of curvature is called the principal axis. Even here we have the optical center, the centers of curvature. Interesting here, C1 is on the right hand side, but here for concave lens, we write it on the left hand side. Why? That I'll tell you soon. Now the radius of curvature is the distance between the optical center and the center of curvature. If both the radii are equal, that means the lens is symmetrical. It's called a equiconvex or equiconcave lens. Now what is this optical center? It is that point on the principal axis such that a ray of light which was directed towards it will get laterally displaced, because this side, so the central region of the lens behaves like a rectangular glass slab. So this ray of light is laterally displaced. The emergent ray is parallel to the incident ray. Now for a thin lens, this lateral displacement is so small that we can consider that a ray of light passing through the optical center comes out undeviated with practically no lateral displacement. So that defines the optical center for thin lenses. Next, the focus point. Now, there are two types of foci. The first focus for the convex lens is on the LHS, whereas for concave it is on the RHS. It is such a point on the principal axis such that rays of light emerging from it after refraction will become parallel to the principal axis. And for concave lens, rays of light incident towards it, means without the lens they would have met here, but because of the lens, now after refraction they will become parallel to the principal axis. Remember, when you draw, you use a ruler, you draw arrows, and the refraction should take place along the axis of the lens, right in the center, not at the surface, but right in the central region here and here. Now when nothing is mentioned, we always assume that the focus being talked about is the second focus, which is practically more significant, relevant for our numericals or our diagrams. It's the second focal point which is important. Rays of light parallel to the principal axis after refraction will meet at a point, and here the rays of light parallel to the principal axis after refraction will diverge away and appear to be coming from a point on the principal axis, and that is called the second focus. So now you know why the focus on for the convex lens is on the RHS here, but for a concave lens it is on the LHS. That's because this is a real focus. Here light actually meets. This is a virtual focus. Here rays of light don't actually meet. Convex lens usually produces real images, which can be taken on a screen. For example, the images thrown by your projector in the cinema halls or otherwise, the images are formed on screen, so they are called real images. Whereas here rays of light don't actually meet and it cannot be taken on a screen. We can only perceive it with our eyes. Such images are called virtual images. For example, the image you see in a mirror, they can't be taken on a screen, so they are virtual images. So convex lens almost always produces real image, except in one circumstance, which we'll study soon. Concave lens always produces virtual images. Now focal plane is that two-dimensional slice of space passing through the focus. So when rays of light are parallel to each other, but not to the principal axis, then they won't meet at the focus, rather they will meet in the focal plane. Now you don't have to draw it, it's not double tick, but if you have to draw such diagrams, three rays are enough. The distance between the optic center and the focus is called the focal length, by the way. For a concave lens also, the rays of light parallel to each other but not to the principal axis, that means they're oblique to the principal axis. They will diverge, but they will not appear to be coming from the focal point, rather they will be coming from a point in the focal plane. Now the focal length of a lens depends on two factors. First of all, what is the refractive index of that medium with respect to the surroundings? For example, this glass lens may have a particular refractive index in air, but if you put it in water, then the focal length will change. The focal length in air was something specific, but in water it increases, because the refractive index of glass with respect to water is different from the refractive index of glass with respect to air. Secondly, it depends on the radius of curvature. If the lens has a small radius of curvature, then the focal length is also small. On the other hand, if the radius of curvature is large, then the focal length will also be large. Now, practically, the refraction actually takes place at two surfaces, first surface and second surface. But we assume the lenses to be thin enough that we draw the refraction only once at the axis point.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.